My esteemed viewers, in continuation with our greedy algorithm design technique, we find remarkably another greedy algorithm for the minimum spanning tree problem that also always yields an optimal solution. It is named as Kruskal's algorithm in honor of the mathematician Joseph Kruskal, who discovered the algorithm when he was a second year graduate student during 1956. Kruskal's algorithm looks at a minimum spanning tree for a weighted connected graph like Prim's algorithm as a acyclic subgraph with number of vertices minus 1 edges. Of course, this is true for any of these spanning trees, because if there are number of vertices to be 4, the number of edges required in order to develop a spanning tree will happens to be 4 minus 1, that is 3. The algorithm, if Prim's algorithm develops the minimum spanning tree, as you have seen in the previous tutorial, by selecting one vertex at a time. Therefore, Prim's algorithm is greedy. It will select one vertex at a time. Once it selects, there is nothing like going back because it is greedy. There is no backtracking. In a similar fashion, this algorithm, and he is the man, Joseph Kruskal, American statistician, and he is responsible for developing this wonderful algorithm which will find out the minimum spanning tree. The important point here is he was a second year graduate then. Okay. Anyway, the algorithm begins by sorting the graph edges in ascending order. Then it scans this list in every iteration. It chooses the minimum weightage. It includes that minimum weightage into the set of edges that covers a minimum spanning tree. It includes this edge if and only if the inclusion doesn't generate a loop or a cycle. Okay, I repeat, it orders all the edges of a weighted graph in ascending order, in the ascending order of the weights. It scans the list in every iteration. It includes an edge, next edge or subsequent edge if and only if the inclusion of this particular edge doesn't create a loop in the spanning tree. Of course, it will fail to be spanning tree if at all it is so. Okay. Now we will just work on the algorithm with the same with a very simple example. Okay, and it goes something like this: 3 edges to start with. There will be nothing. Okay, to start with there will be nothing. So therefore we will just keep a blank over here, and now sorted edges will come something like this: BC is the edge with weight 1. Then comes DE with the weight 2. The algorithm has to look simultaneously with the weight matrix, and it has to arrange this. There is no other go. Okay, BD is the next edge with 3 as the weight, BD. Then comes CD with the weight 4. Okay, then comes BA or AB with the edge weight 5. Then AD is 6. AD is 6. So also CE is also 6. Naturally, it has to choose BC. So BC is chosen. BC is included as a part of the minimum spanning tree, or as a subgraph of the given graph, as a part of subgraph. So this is over. Next, in the next cycle, it will select DE. So okay, by selecting DE, there is no question of formation of the loop. Therefore, it chooses DE. So DE is 2. Okay. Then it has to choose BD. Okay. So BC is selected, DE is selected, and BD can be selected because there is no formation of the loop. BD is also selected, that is 3. Weight is 3. If we start writing the development of this spanning tree, here it goes. B is here, okay, then C, BC is the first edge that was chosen, and DE was the next edge that was chosen, okay, DE, then BD is chosen, okay, this was 1, this is 3, this is 2. Okay, 1, 2, 3. 3 edges have been already chosen. Here there are 5 vertices. Therefore, we need to select one more edge so that it becomes 4. Okay, in a spanning tree, the number of edges you have to remember. Please remember the number of edges will be what number of vertices minus 1. So the next alternative is CD. If you select CD, it will essentially generate a cycle over here. B, C, D, B. B, C, D, B, a cycle will be generated. Therefore, there is no question of selecting CD. Or AB, if we select AB, it incurs no loop. Therefore, AB has to be selected. And that is also the minimum among the remaining. Okay, minimum weighted edge among the remaining edges. Okay, therefore, A comes somewhere over here. This is how the spanning tree is developed, and this becomes 5. Therefore, the minimum spanning tree weight is 1 plus 3 plus 2 plus 5, 11 units. Okay, keeping this in mind, we'll solve yet another example. Of course, it's a big graph. Anyway, I have not chosen to write the table again. Anyway, it becomes primitive. Okay, my respected viewers will definitely construct a table and definitely do in the iterations, in the iterative fashion. Of course, this algorithm needs v minus 1 iterations, where v is the cardinality of the vertex set. Okay, therefore, in that token 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 vertices. It needs 11 edges in order to construct the minimum spanning tree. Okay, minimum spanning tree, and it also incurs 11 iterations. The algorithm incurs 11 iterations. Okay, this is the first one that is selected, first edge, because the weight is 1. Then these two edges are selected. Okay, CD as well as EF. Okay, then CB is selected, that is 3, and BA is selected. And selection of these two sides, these two edges will never incur in the development of the loop, therefore they are selected. And GH and IJ is selected, so it's already 1, 2, 3, 4, 5, 6, 7. 7 edges are already there. Okay, this is the one, next one, GC. So 8, this is 9, 10, 11. So that completes the minimum spanning tree. You have to add and you have to just put it. We will write the algorithm. Okay, what it does, it constructs a minimum spanning tree using Kruskals algorithm. Input is a weighted connected graph G, which is set of sets. One of the sets is vertex set, the other set is edge set. Output is EMST, that is edges constituting minimum spanning tree. Edges constituting minimum spanning tree. The set of edges comprising the minimum spanning tree of G. Sort the edges. The first step is sort the edges in ascending order of their weights. Then EMST equal to 0. It should ensure, because to start with there is no spanning tree yet. Therefore, the edge set of the minimum spanning tree consists of 0. Therefore, it is initialized. Edge counter is another counter which will maintain cardinality of v minus 1 cycles, that is number of vertices minus 1 cycles. Okay, it will keep a track of how many iterations the algorithm must have done. K equal to 0, this is initialized the number of processed edges. Okay, how many edges are processed while before it is included, before the minimum minimum weight edge is included. Okay, here is a while loop. While edge counter is less than cardinality of v minus 1, that is number of vertices minus 1, so k equal to k plus 1. Okay, one of the edges is already processed. Okay, if EMST union EIK, the first edge, okay, k equal to k plus 1, k is 0. Okay, the first edge is to be selected anyway, so this is the first edge. That is, if EMST union EIK is acyclic, okay, then EMST equal to EMST union EIK. So EIK is union with this particular set. Now EMST, okay, EMST consists of EIK, that is the first edge, and edge counter will be incremented in order to keep regard of whether we have crossed the limits of number of vertices minus 1. It should be within that. Okay, edge counter plus 1, so it will be cyclically going through till okay, this is satisfied. Edge counter will be less than cardinality of vertex minus 1. Okay, so this is the algorithm. Now there are two important points that is to be remembered, that is to be noted down as far as minimum spanning trees are concerned, irrespective of the algorithm that we are going to use. This is fundamental thing about minimum spanning trees. If E is a minimum weight edge in a connected weighted graph, it must be among the edges of at least one minimum spanning tree of the graph. Okay, if at all you can draw several minimum spanning trees, let us say 1 or 2 minimum spanning trees, because of the repetition of the weights, and if E happens to be the minimum weight edge, definitely it should be there in any one of the spanning trees. That is the meaning of this particular paragraph. If edge weights of a connected weighted graph are all distinct, if all the weights are distinct, they are different, okay, the graph must have exactly one minimum spanning tree. If all the weights are different, okay, if some of the weights are equal and if they happen to be minimum, you may get 2 or 3 minimum spanning trees, but anyway the minimum edge weight will be there at least in any one of them. Okay, let us say there are 3 edges with weights 2, 2, 2. Okay, so one of them will be definitely there in one of the minimum spanning trees. The second case is all the weights are unique, all the weights are discrete, or they are different, they are distinct, therefore are unique, therefore there can be only one minimum spanning tree. That is the meaning of this. Now there is one classical problem which should not miss our attention. 4 villages are located at the vertices of a unit square in the Euclidean plane. You are asked to connect them by the shortest networks of roads so that there is a path between every pair of the villages along those roads. Okay, let us assume, okay, let us try to understand this particular classical problem. Let us assume that the length of, okay, it's a unit cube, okay, unit square, let us say, all the sides are equal, that is the meaning of this. Okay, 4 villages, you are asked to connect them by square in a vertices of a unit square. Okay, it's a square of unit dimension. Anyway, we will assume it to be 10 meters. Okay, now the minimum spanning tree is this only. We cannot draw diagonal lines, because diagonal lines will measure much more than 10. Okay, this is the minimum spanning tree, 10 plus 10 plus 10. That is the weight. But we can draw a spanning tree, okay, which is a classical spanning tree, which is much lesser than this 30 units of distance or 30 units of measurement. So this is the Steiner's tree. Okay, the angle here are 120 degree, and here this is 30 degree. Anyway, this is 120, and this is a equilateral triangle. Therefore, this will become no, it's a isosceles triangle. This will become 30, and this will become 30. And if you take what is it, cosine 30 or tan 30, okay, and we will get this length to be around 2.9 meters. 2.9, because tan 30 is tan 30 is opposite by adjacent, we will get this as 2.9. Here also there is 2.9, in similar fashion 2.9 meters. Therefore this length happens to be 10 minus 2 times 2.9. So this will be 4.2 meters. 4.2 meters. In the same token, this forms the hypotenuse of this particular triangle with sine 30. Okay, with sine 30 as the trigonometrical unit, we will find sine 30 equal to 2.9, that is opposite by hypotenuse. Therefore we will get the hypotenuse value to be 5.8. This will become 5.8 units or 5.8 meters or whatever. Okay, I repeat, sine 30 equal to opposite by hypotenuse. Hypotenuse is not known to us. By using tan 30 we have calculated this particular length, and we have also calculated this particular length. In order to obtain this hypotenuse, we have taken sine 30. So sine 30 is opposite by hypotenuse, we will get 5.8. Okay, therefore the minimum spanning tree now is there are 1, 2, 3, 4 sides of 5.9 each, and one of 4.2 meters. Okay, therefore this would amount to the minimum spanning tree over here. Of course there are no vertices over here, therefore it is a special tree called as Steiner tree. And if I have the budget of connecting all the villages, 4 villages, with a distance, I can construct a road. Let us say the project envisages of construction of a road which is much lesser than 30 meters, then the spanning tree will never answer the question. Okay, so this becomes 23.2, because this is governed by the rule, the existing budget, the available budget 4.2. Okay, this will take us to around 27.4 meters. Of course there is a saving of around 2.6 meters. Of course if the length cannot be in 10 meters, in meters, like, okay, in the units of measure as meter, it will be to the tune of kilometers. Therefore there is a substantial saving if at all the budget is limited. Okay, and you can develop some kind of a special kind of a spanning tree, of course, with only 4 vertices. The speciality of this particular spanning tree is, if at all it is to be called as a spanning tree, is the number of sides happens to be 1, 2, 3, 4, 5. There are one more than the number of vertices, 1, 2, 3, 4, 5. But anyway, it is yielding us less distance or real minimum value. Okay, this may be called as an optimal minimal spanning tree. So with this we will conclude. Okay, we will, in our next video we will just talk about another algorithm based on greedy technique, coming to be called as single source shortest path problem. Okay, the concerned algorithm is Dijkstra's algorithms. Until